All right, this video we're going to be looking at integration by substitution. First of all, let's just review the difference between a definite integral and an indefinite integral. The definite integral is a number. It's going to end up being a number, and it's going to represent the area between the curve and the x-axis. And the indefinite integral is a family of functions that have the same derivative, and that's when you end up with a function plus c. We do the same thing for both cases. We're going to find the antiderivative, but with the definite integral, you're going to put in your upper limit of integration and subtract the lower limit of integration from that. Okay, so we're going to, like I said, we're going to be using substitution to integrate these integrands, and we're going to want to look for patterns here. So I'm just going to do some examples. Hopefully I start to catch on here. So what you're looking for when you're looking for a pattern is you're looking for a part of this integrand whose derivative is also a part of that integrand. So it's called u-substitution. If we let u equal this inside piece here, so I have that right here, then du would be 2x, the derivative of u with respect to x, the differential, would be du equals 2x dx. Now notice I have a 2x dx here, so I can make this integral, and this is an indefinite integral. I'm going to switch the location here using a commutative property. Now, if you look at this, I can replace the x squared plus 1 with u. So I have u to the fourth, and then I can replace this piece with du. And now I simply need to integrate u to the fourth with respect to the variable u. So we're actually taking a fairly complex integrand and we're making it look easy. Okay, so we integrate this with respect to u, so you add 1 to the exponent, and we're going to divide by that. And I'm going to have a plus c here because this is an indefinite integral. And then I need to sub this back in, I need to sub this u, what I had for u here, back in here. So I end up with x squared plus 1 to the fifth over 5 plus c. Okay, let's do another example. So look at this, and so there's no rule for product or quotient. Like you can't take the antiderivative of each piece and then, like, let me back up here. You can't take the antiderivative of 2x and then the antiderivative of x squared plus 1 to the fourth and then just multiply those together. There's no rule for a product or a quotient. So for this problem, I want you to think about what you might want to let u equal so that you see a piece of the derivative in that integrand as well. Hopefully you're seeing that x squared minus 4 almost has the derivative here. If I find the derivative of x squared minus 4, if I let u equal x squared minus 4 and then I find du, it's equal to 2x dx. Well, I can split this guy up here and notice that this is a definite integral. I can write this as 1 over x squared minus 4, and then move the x over, because if you think about, like, if I multiplied back through, I'd get this, what I started with. I don't have 2x dx, I just have x dx. So what I can do, though, because I'm just missing a constant, not a variable, that's an important piece, I'm missing a constant, I can multiply by 2 inside here. If I do that, I'm changing this, so I need to also multiply by 1/2 or divide by 2 so that I'm not altering the value of this. So now I have the du right here. So I can rewrite this. I have this 1/2 on the outside, and I have from 0 to 1, and then I can put this in as 1 over u, and then 2x dx is equal to my du. And so I'm just going to integrate 1 over u, which this is kind of just a memory test here. You have to, when you have 1 over u, it's the ln of absolute value of u. I don't, This is going to fail here because I have a limit of integration that is equal to, oh wait, actually, no, that's equal to 0, which isn't going to work because the ln is defined, but we're doing the absolute value. So let's look at this. So we have 1/2 ln, I'm going to throw in my u, which was x squared minus 4, and from 0 to 1, and then that's going to equal 1/2 ln, if I put 1 in here, in absolute value, so we didn't have the absolute value, I'd be in trouble here. 1 squared is 1, minus 4 is -3, and then minus, I'm going to have to multiply the 1/2 times this whole thing, so I'm going to put parentheses around that. ln of 0 minus 4, 0 squared. So that becomes 1/2 ln of the absolute value of -3, ln of 3, minus ln of the absolute value of -4, which is 4. That works right there, but you can rewrite that as 1/2 ln, because I can, and it was 1/2 times this whole thing. I didn't put my parentheses around there. When you have subtraction, there's a property of logarithms. Hopefully you remember the quotient property. It's ln of 3/4. Okay, so this could be written as ln of 3/4 to the 1/2 power, because I can bring this, the power property of logarithms, I can bring that exponent back up, and 1/2 power is the same thing as the square root. So you might, if you saw a multiple choice test question, something like this, you might have this answer. You can also take the square root of 4, so it could also look like this, square root of 3 over 2. ln of the square root of 3 over 2. All right, let's do a couple more here. Think about what you would equal here. Maybe try to do this problem and then come back and do it with me. So we have my u is going to be this part that's underneath the square root, so x cubed plus 1, and then my du will be 3x squared dx. So rearranging this, and this is a indefinite integral, I'm going to put x cubed plus 1, square root is 1/2 power, I'm going to have 3x squared dx. So I'm going to have u to the 1/2. All of this is equivalent to du. So I've just made this complex integrand look really simple. I'm going to add 1 to the exponent, and I'm going to divide by 3/2, which is the same as multiplying by 2/3. And then I have plus c, and I'm going to put my u back in here, so my final answer is 2, and then my u is x cubed plus 1 to the 3/2 over 3 plus c. Okay, let's do one that has a trig function in it. So here we have sine of x times cosine of x. Sine of x has a derivative of cosine of x. Cosine of x has a derivative of negative sine of x. So actually you could let either sine of x or cosine of x be u. But if I let u equal cosine of x, then I'll just do this, and it'd probably be easier to let u equal sine of x, because you save this one step here. The derivative of cosine is negative sine of x. And notice there's no negative here, which means I'm going to rearrange this first of all. I'm going to put the sine of x over here. But I need it to be negative sine of x, so I'm going to multiply by a negative here, which means I need a negative on the outside. If I could have avoided that negative if I would have let u equal sine of x. So then this becomes negative u, because cosine of x is u, and then this is my du. So integrating u is, I got that negative from here, and then the antiderivative of u is u squared over 2. And I'm going to put my u back in, and I get negative cosine squared x over 2. All right, that's it for today.